So the clipping is is very simple method to reducing the PAPR. Uh, but the efficiency is not very high, and also it increased bit error rate. This is the second method, selective mapping. The basic idea is to add some phase vector to the original signal and do multiplicating and find so there will be a lot of new signals with the phase vector, and I choose the smallest PAPR as the signal I will transmit, and then as the receiver, I will do the division for the original signal to find the original signal. This is the result of simulation. We can clearly see that SLM is a very efficient method to reduce PAPR. For example, for PAPR equals to 7 dB, the probability larger than 7 dB of original signal is about 10 times minus 0.5, and after SLM with 16 factors approaching, the probability decreased 2 times and 10 times minus 2. And this figure shows the signal after SLM. You can clearly see that the red signal is after doing SLM. It is more concentrated, so the average is near to the peak. So the PAPR reduced a lot. We can see the original signal, even though there is only some peaks, but the average is not very high, so the PAPR is very high. And then I do some comparisons with different SM vectors. I can see the more vectors I use, it means the more randomness of the signal I approach. So the PAPR can reduce a lot. For clipping, the problem is the signal is distorted, so the BER increase a lot. But for SLM, we just add some vectors to reduce PAPRs, so the bit error rate does not change much. The third technique I use is the partial transmit sequence. This method is based on phase shifting to set block of data, then do the multiplexional data structure by random vectors, just like SLM. But for the PTS, the input data block of n symbols is separated in many sub-blocks. It's decrease the complexity of calculation comparing to the SLM. And then just like SLM, choose the minimum signal, minimum PAPR of the combined signal as the output. This is the result of this simulation. I can see that PTS is also a very efficient technique to reduce the PAPR. For PAPR equals to 8 dB, the original CCDF is 10 times minus 0.5, and after PTS approach, the probability decreased to 10 times no minus 1.8. This is the signal signal compared results always PTS. Also, the red signal is more concentrated, and there is few peaks, and the average is larger than the original one. For PTS, the bit average not change much because it is also a method to increase the randomness of the signal, so the signal is not distorted. And also the PTS reduce the complexity of the system. Conclusion. 3 PAPR reduction techniques are discussed as the clipping, SLM, PTS in this project. The clipping is the simplest method to reduce PAPR because it just uses a filter to filter the peak power signal. However, low efficiency and high bit error rate is the drawback of clipping. Both SLM and PTS are important probabilistic scheme for PAPR reduction. The basic idea of them is both increase the randomness of the signal, define the small PAPR. SLM can produce independent multiple frequency signals. However, lots of IFFT operations are not available. PTS divides the frequency vector into some subblocks before applying the phase transformation. Some of the complexity of doing full IFFT operations can be avoided. In this case, it is more advantageous than SM if amounts of computational complexity is limited. Related work. There are many other techniques are used for reduction of PAPR in OFDM system as tone reservation, tone injection, active constellation extension, and so on. For TR, adding time domain signal block to the original signal. The complexity of calculation of is low and the low distortion of the signal. However, if there are a few subcarriers, the efficiency of the spectrum is low. And for TI, using the correction vector to reduce PAPR, the efficiency of spectrum is high, but the energy will lose in transmission. For ACE, the method is like DI. Low bit error rate is pro of this method. However, for large constellation, it is hard to implement it. This is the presentation, and then I will do the simulation of my project. This is the original signal. And this one is the signal I used to approach in the 3 method. This is the CCDF, This is the signal. This program is using clipping. You can see that this is the signal after clipping, the red one. And this is the CCDF with different vectors. This is the big array. And I'll show you the SRM. This is the signal after doing SRM, the red one. This is the conversion of different SRM vectors. This is the big array of the SRM system. This is PPS. See. This is the CCDF simulation. This is the array. Okay, thanks for listening. Thank you very much.